All right, here's our review for gravitation and electrostatics. For number one, I'm going to let you go back through that big note packet and do this on your own. But I need you to remember, it's important. You have a note packet that you can look through to find all that stuff out from. I don't need to revisit that. Compare and contrast the force of gravity with the electrostatic force. Both are inverse square laws. Meaning that that force is somehow proportional to 1 over r squared. Both can be attractive, and they do look alike. Those are some of the similarities. Some of the difference: the electric force in general is greater than the gravitational force, and the reason we said that is because the constant K is much greater than the constant capital G, those proportionality constants. And the electric force can be repulsive as well as attractive. Gravity can't. How did Henry Cavendish measure the universal gravitation constant? So what he used was an extremely sensitive device called a torsion balance. In a torsion balance, what you have is a really heavy object, another really heavy object that are being balanced on a board or a bar. That bar is attached to a string, and then we bring another mass close to it and another mass close to it, and those blue masses cause the entire system to torque or to spin around it. And so what this allows us to do it allows us to measure force, mass 1, mass 2, and the radius so that we can solve for G. And it had to be extremely sensitive because it was dealing with extremely small forces. Describe the relationship between the force of gravity, mass, and distance. This is Newton's law of universal gravitation. The force of gravity is G times mass 1 times mass 2 over the distance squared. It depends on the size of each mass. And it depends on the distance separating them. Describe the relationship between the electric force, charge, and distance. So for this, for the electric force, we have K, Q1, Q2 over the distance separating them squared. We can see here that it depends on the size of the charges, and it depends on the distance separating the charges. Describe how induction occurs. So our basic steps are polarize, remove excess charge. That's all we have to do. So if we have an object that begins life neutral, so this would be step 1. We have an object that begins life neutral, and then we're going to bring something charged close to it. So this is negatively charged. What's going to happen is that this thing polarizes. So all the positive charges are attracted to that negative charge. All the negative charges go away. So here is our polarized step. So that's our polarized step. So while it's polarized, what we want to do is to remove some of that excess charge. So some of those negative charges are going to go away. And that brings us to step 2. Once we remove those excess charges, all the positive charges are still there. But we have fewer negative charges. So this thing is left positively charged, because it has more positive charges than negative charges. What's the smallest value of charge other than 0 that an object can have? And then can charge ever be created? Smallest value is 1 electron or 1 proton. I can't move fractions of an electron. So an electron is as small as it gets. Charge is created in some nuclear reactions. That's how we're going to say it. We're a little bit more detailed on the other sheet. But net charge is never created. So in those situations where we create charge, and again, that's a nuclear reaction. That's not running a brush through your hair. In those situations where we create charge, we are separating, well, we're creating positive and negative equally. When we charge an object, when we do that, we move positive and negative charges apart. That's what it means to charge an object. We're moving charges around. We're not creating charges, we're just moving them around. Number 8, 2 spheres are separated by 40 meters. Sphere 1 has a mass of, it's kind of hard to see. Sphere 1 has a mass of 8 times 10 to the 5th kilograms and a charge of 4 times 10 to the negative 6th coulombs. Sphere 2 has that mass and that charge. Calculate the gravitational force between them. Is it attractive or repulsive? Gravitational force is g times mass 1 times mass 2 over radius squared. So it's going to be 6.67 times 10 to the negative 11th times mass 1, which was 8 times 10 to the 5th, times mass 2, 3 times 10 to the 6th, divided by the distance separating them, 40 meters squared. So to calculate that, and again, we're gonna use the calculator to do it. So 6.67 times 10 to the negative 11th times 8 times 10 to the 5th times 3 times 10 to the 6th divided by 40 squared. So the gravitational force comes out to be 0.1 newtons. So that's our gravitational force, and gravity is always attractive. So for these two masses, sphere 1 and sphere 2, the gravitational force is towards each other. Calculate the electric force between these two spheres. Okay, so for the electric force is kq1 q2 over the distance separating them squared. So we have 9 times 10 to the 9th times q1, 4 times 10 to the negative 6th times q2, 6 times 10 to the negative 6th divided by that distance of 40 meters squared. So we'll use the calculator again because I want to show you all how to enter this. 9 second, comma 9 times 4 second, comma, so that's 4e, negative 6 times 6 second, comma, e, negative 6 divided by 40 squared. And so that force comes out to be 1.35 times 10 to the negative 4th newtons. And here, what we see is that this is going to be repulsive because both charges are positive and like charges repel. How would your answers to A and B change if the following changes were made? So if I doubled mass 1, first of all, changing the mass makes no change to the electrical force. So I'm going to go through, doubling the masses makes no change to the electric force, and doubling the charges makes no change to the gravitational force. So if I double mass 1, I'm going to highlight that. If I multiply that by 2, I am going to double the gravitational force. No change to the electric force. If I were to double charge 1, charge 1's right here. If I were to double that, I would double the electric force, so twice the electric force. If I were to double both masses, so instead of just one mass, I've got both of them that are doubled. If I double both masses, I increase the force by a factor of 4. And again, changing the masses doesn't really affect the electric charge, and then the electric force. And then if I double both charges, same deal. Multiply the top by 2, multiply the top by 2. The top has been multiplied by 4. That is 4 times the electric force now. Okay, so now for distance, come through here, I'll do a different color. If I double the distance, well, that's going to affect both of them. So it's distance squared. So that means I'm going to be dividing each thing not by 2 but by 4. So I'm going to have 1/4. Well, that's just not writing well at all. I'm going to have 1/4 the gravitational force and 1/4 the electric force. And then if we triple the distance instead of doubling it, we're not dividing by 3, we're dividing by 3 squared. So I'm going to have 1/9 the gravitational force and 1/9 the electric force. Determine the acceleration due to gravity on this other planet based on these numbers. So to get acceleration due to gravity, I know that the force of gravity is equal to gm of the planet, mass of the object over the radius of the planet squared. But I also know that the gravitational force is equal to the mass of the object times the acceleration due to gravity. So looking at both of those, the mass of the object crosses out. So the acceleration due to gravity is g times the mass of the planet divided by the radius of the planet squared. So 6.67 times 10 to the negative 11th times the mass of the planet, 5.98 times 10 to the 24th kilograms, divided by the radius of the planet squared, 6.38 times 10 to the 6th meters, and then that whole thing is squared. Again, we're going to need to use the calculator to figure this out. So 6.67 second E negative 11 times 5.98 second E 24 divided by 6.38 second E 6 whole quantity squared. That's entered in the right way. It's going to do all the right things. And so that comes out to be 9.8 meters per second squared. That seems familiar. Two charges are separated by 0.2 meters. We have one of the charges, we don't know the other charge, and we know the force between them, and I want to know the second charge and indicate if it's positive or negative. So to get the charge, I know that the electric force is equal to K Q1 Q2 over the distance between them squared. So if I want to solve for Q2, I need it all by itself. The first thing I want to do is get rid of the R, so I'll multiply both sides by R squared. So that gets rid of it on the right side. And I want Q2 all by itself, so I'm going to divide both sides by Q1. The Q1 goes away on the right side, and then divide both sides by K, so the K goes away on the right side. So this tells me that Q2 is equal to R squared times the electric force divided by K times Q1. So based on the things that we have, we are separated by 0.2 meters squared. Our force is 200 newtons divided by K, 9 times 10 to the 9th, Newton meters squared per Coulomb squared, times Q1, which we know is 5 times 10 to the negative 5th coulombs. So, again, we're going to put all of that into our calculator. 0.2 squared times 200 divided by 9 times 10 to the 9th times 5 times 10 to the negative 5th. Check it to make sure everything's right, and then we enter it. And so that charge comes out to be 1.78 times 10 to the negative 5th coulombs. So Q2 is 1.78 times 10 to the negative 5th coulombs. That's the size of the charge, but if I want to know if it's positive or negative, we need to look at what's going on. They attract each other. Opposites attract. Charge 1 is negative, so charge 2 must be positive because those opposite charges attract each other.